Alrighty guys, so the next part of learning target 1 is graphing logarithmic functions. And to be able to graph a logarithmic function, we need to know what that function is. So we're going to start by revisiting inverses from Algebra 2. So an inverse kind of tells us the undoing of a function, right? If you think back to Algebra 2, we would switch the x and y's and solve for it. We would isolate the other variable. So inverses are basically an undoing function. Okay, here are some things that we know about inverses. Maybe you know them from Algebra 2, maybe you're just learning them now. The first one is that the domain and range flip-flop for functions and their inverses. So the domain of a function is the range of its inverse. The range of a function is the domain of its inverse. Okay? Within that, all of the ordered pairs are switching, which is what that third bullet point means. It basically means if I have the point A comma B on f of x, then I'm going to have the point B comma A on f inverse of x. Right, so the domain and range switching is literally every single x-y pair is flip-flopping. Visually, it looks like a reflection across the line y equals x. In order for a function to have an inverse, it has to be one-to-one. And that means that it needs to pass the vertical and horizontal line test. So not only does every input need to have a single output, but every output needs to have a single input. Okay, in Algebra 2, when a function was one-to-one and we found the inverse of it, we would switch x and y, solve for the new y, and then replace y with f inverse of x. Okay, so I want to find the inverse of an exponential function. Exponential functions have inverses. They are one-to-one. But what happens when I switch x and y? I get something that I can't solve. But it is a function. It does exist. I could graph this. I could find ordered pairs and graph this, but I can't solve for y. And in order to graph a function and work with a function, we always want it to be y equals. Right? I can't take the y-th root of both sides. I can't divide by 5. Nothing is going to isolate y, but like this is a thing. This does exist. So that is where logarithms come in. Logarithms are born because they are the inverse of an exponential function. So instead of writing it as here, x equals 5 to the y, we'll be able to write something equivalent to that, because it's also an inverse, that has to do with logs. So a logarithm actually calculates the exponent, right? When we're solving exponentials, we are calculating what happens when we raise a base to an exponent. When we're calculating a logarithm, we're solving for the exponent that goes on the input to get on the base to get the input. Okay, so exponential and logarithmic functions are inverses. This is the parent function for a log, and we would say this as y equals log base b of x. That's how you're going to say it. And because it's the same as the exponential function, b still has to be greater than 0 and b cannot equal 1. This is what a logarithmic function looks like. The base can be anything so long as it's positive and not 1. And again, we say this is y equals log base b of x. And when we go to graph logarithmic functions, this is our parent function. This is what we're going to start with. Okay. The relationship between logarithmic functions and exponential functions, obviously they're inverses, but switching back and forth between them is a really, really helpful tool. Honestly, I think this is a little easier of a way to think about it. Now, we said that if I started with an exponential function, so if I started with the exponential function b to the x equals y, right here, b to the y equals x, is what would happen if I found the inverse of it, right? I switch my x and y coordinate. That's what we do to find an inverse. Well, b to the y equals x, again, is not in y equals form. That is where logs come in. This is equivalent. This is equal to what I have right here. So b to the y equals x is the same as y equals log base b of x, whereas both of these are then inverses of b to the x equals y. This is really difficult to calculate. You actually can't put it into your calculator unless it's a common log with a base of 10 or a natural log with a base of e. Those are the only log buttons on our red calculators. If I want to do anything else with a different base, I need to think of it as an exponential because exponentials are things that I know how to solve. So that's what we're going to do when we go to graph our logarithmic functions. Okay? So looking at this, if I was graphing an exponential function, I would start with my parent function, a 5 to the x. I would input and then I would vertically shift it up to. Well, if I wanted to graph y equals log base 3 of x, I can't just input values for x because first of all, I can't type them into my calculator. Log base 3 of 5, can't type that into your red calculator, which is what you guys can use on tests. So I need to think of it in a different way. And again, we talked about this on a previous slide. When I'm solving for a log, that means I'm solving for the exponent. So when if I did log base 3 of 5, if I said, okay, log base 3 of 5, I input 5 to my function. That is asking what is the exponent that I put on 3 to get 5? And that's going to be a decimal. It's going to be a weird number. That's another reason we have to be careful with logs. It's really hard to get nice numbers out of it. So to avoid all of that confusion, what we can do is just switch it to exponential form and instead input for the y coordinate. So if this is the parent function I'm given, right, with a base of 3, I'm going to change it to 3 to the y equals x using this property right here. And this is one of the most important properties in this unit. We'll use it in LT1, LT2, and LT3. Okay, so for example, if I wanted to take log base 4 of x equals y, I can change that into 4 to the y equals x, right? I like to draw like a little circle. 4 to the power of y equals x. Here, my base is going to stay the same, so it's going to be log base 6, and my input and output switches, right? Remember with inverse functions, your inputs and outputs switch. So it'd be 216 as my input now, and x as my output. And then this one, 2 to the 5th, equals 32. Okay, so this property we can use to get ourselves some nice starting points because now I know, okay, 3 to the negative 1 is 1/3, 3 to the 0 is 1, 3 to the first is 3. I can now graph this function using transformations because I have my starting points. And that's exactly what we're going to do. Okay. Yesterday, we looked at the general shape of an exponential function. Here's the general shape of a logarithmic function. The important thing to note from this is that the parent function, the general shape, has a vertical asymptote now. It always starts at x equals 0, and however x is transformed is how the vertical asymptote is transformed. Okay. You can see that they're a reflection of each other. So 2 to the x and log base 2 of x are inverses of each other, where this is the same thing. If I did 2 to the y equals x, that would end up being the same thing. But you can see they're reflected across the line, y equals x. But doing reflections and making them exact can be kind of difficult. So oftentimes that's more just to like see if your answer makes sense rather than a method for doing it. Okay, very important. I feel like we've seen this slide quite a few times. If you have not written it down at this point, go ahead and pause and write it down because this is a very important slide. All right, here is an example just showing you that the transformations of functions work exactly the same way that they worked with exponential functions. So I have log base 4 of x plus 1 minus 4. My parent function is going to be 4 to the y equals x. I'm going to input negative 1, 0, and 1 into my y because that's what my exponent is. And then I'm going to evaluate my x values there. So I started with inputting, all these values, and these were my original outputs. Okay? It's flip-flopped because inverses have flip-flopped inputs and outputs. But notice the transformations work the same. Here we have something inside the function. Inside the function is a horizontal transformation, and we always do the opposite operation. So you can see that we took our x's and we subtracted 1. Then we have a minus 4 on the outside of the function. Just like with exponentials, on the outside of the function, it's considered a vertical transformation, and we do what it says. Okay, so we subtracted 4 from all of our y values. That gave us our new points. I'll mention real quick, my vertical asymptote would have started at x equals 0. Then I subtracted 1 from all my x's. So now it's x equals negative 1. And you can see my function does go straight along the asymptote, but it's growing forever. It's going up forever still. Okay? So the range, it's going down forever and up forever. My range is actually going to be negative infinity to infinity. Okay? Go ahead and pause right here and write these steps down. They are very, very, very similar to the steps for exponential functions. Really, the first step is the only thing that's different, the first and second step. When you're applying transformations, you do them in the same order, in the same way. Same exact thing, right? With horizontal, it's inside the function. You do opposite operation and reverse PEMDAS. For vertical, it's outside the function, which in this case is outside of the log. It is PEMDAS order, and you do the operation given. Okay? These are the steps. Here is some information about the asymptote. I talked about it on the other slide, though. And here's some information about the domain and range. So in this case, the range is always all real numbers, right? The range is going to be all real numbers because the domain of an exponential is all real numbers. And we know that inverse functions, inputs and outputs switch. Okay? There are no outputs that can't be created with the inputs, but that's kind of weird to think about. So usually I just think of it as the opposite of exponential. The domain is going to be from the asymptote to the left or from the asymptote to the right forever. It's just going to be depending on if it is reflecting or not. This is because you can't take the log of 0 or a negative. And we'll talk more about that in LT3, but essentially you're either going to have asymptote to infinity or negative infinity to asymptote. This is if it's going left forever. This is if it's going right forever. Okay? Again, the order of operations, it's the same. Here is a slide that tells you, and this is also in the slide, so you don't have to pause the video to write it down. You can just go to the slides to look at it. This tells you what the transformations mean visually. This kind of tells you the steps to do it algebraically. Okay, the next thing I'm going to have you guys do is watch a video on examples of graphing. So this was kind of an introduction, a little faster than I normally go. I really like logs, so usually, I drag it out. We spend a lot of time discovering them. But this was more an introduction to what a log is, which is the inverse of an exponential. And then the next video you guys are going to watch takes you through step-by-step examples of how to actually graph a log. Then you'll have some time to practice with some worksheets to see if you know what you're doing.